Hi everyone. I'm really excited to welcome you all as we kick off the first of the year, first engineering solutions of the year for our Smart Create community of practice. It's really awesome to see so many of you here and ready to share insights and explore innovative solutions. And for those who don't know me, my name is Olivia Wu. I'm really excited to be here as your new chair, taking over from Dak, who has been instrumental in leading this forum, and he has shared incredible insights. So thank you so much, Dak, for everything you've done. And a little bit about me. I come from a structural engineering background, having worked in consulting before transitioning into my current role as a product portfolio manager at Reid. I'm also the vice president of the Concrete Institute of Australia Victorian Committee. For myself, my passion has always been about bringing innovative and practical solutions to the industry. And it's awesome to have the opportunity to actually focus on exactly that in all the roles that I have, and really looking forward to working with all of you in this forum. I think this COP is such a fantastic space for knowledge sharing, fostering innovation and best practice, and also encouraging collaboration. Now, I think with the diverse perspective we all bring, this platform will continue to help accelerate the development and also the adoption of engineered solutions. I guess we'll dive into today's topic, innovative footing for lightweight structures in expensive soils. A little bit about the background first. As you know, concrete slabs used in housing built on expensive soil face significant challenges now, particularly with heave issues, as expensive soils are highly sensitive to moisture variations. So this issue can lead to severe structural damage and costly repairs for the homeowners. And in addition to that, with climate change expected to bring even more unpredictable weather patterns, now the need for innovative solutions in this space is becoming even more important. And so for today's session, we bring together experts to explore an innovative hybrid footing system that combines waffle piles and screw piles to minimize structural damage and reduce carbon footprint. The project partners are ACSEV, Association of Consulting Structural Engineers Victoria, also FFSV, Foundation and Footing Society of Victoria, as well as Swinburne University. So we have four speakers, four presenters representing the project partners, and the FFSV as well as ACSEV, they intend to modernize building codes and practices to adopt innovative hybrid footing system. Now, before we kick off the presentation, just a few quick housekeeping reminders to make sure the session runs smoothly. First of all, please stay on mute during the presentation to avoid background noise. Like I mentioned before, we have a jam-packed agenda for today with four amazing speakers. At the same time, we do have a hard finish. So we'll have the Q&A session at the end. So please hold your questions until then. However, feel free to drop your questions in the chat anytime, and we'll get to them during the Q&A session. All right, let's dive in. It is my pleasure to introduce our first speaker, Luke. Luke, he's a highly respected soil engineer with 20 years of experience in the field. His expertise spans a wide range of specializations, including greenfields, commercial, rock coring, land capabilities, slope stabilization, as well as pavement and road designs and site surveys. Luke is an active leader in the industry, serving as a committee member and previously the chairperson of the Footings and Foundations Society Victoria. He's also a member of the Association of Consulting Engineers Victoria, and he's the project manager for the Screw Pile Research Project. Luke collaborates closely with professional consultants, civil construction engineers, and is well known and highly regarded in the industry. So please join me in welcoming Luke, who will share his insights and expertise with us today. Over to you, Luke.
Thank you very much for that, Olivia. I'll just set up my share screen. Okay, so thank you for everyone for turning up today to have a look at the project that I'm involved in. So to start off, I'm a geotechnical engineer in my background. We have Russell, who's a structural engineer in his background. We have Biju, who's a structural engineer and also research through university. And we also have Rajeev, who is from Swinburne University as well. And I'll just start off by saying that you're going to have various different ideas, thoughts and opinions from the different presenters today. And in the groups that we're involved with in FFSV and ACSEV, we really welcome different ideas and different thoughts, but I will say that they're each individual presenter's own thoughts. They're not necessarily the group's thoughts. We, as groups, love innovation and creative thinking. And up until now, partly as not-for-profit organisations, our aim has been to better society, to better our practitioners, and to better the product that we deliver to all. This idea of this project actually started from my perspective, coming from Russell Brown, who will be the next presenter. And it was in some committee meetings and general meetings where Russell spoke to me and others about what we could do to create a better system than what we currently have that leads to issues and failures. It made sense to me because understanding soil from my understanding and how I think about it, brings it back to a chemistry basis, because what water does to soil is what affects it. And that change in what that water does to it gives us various movements and various issues. We are now getting lots of sites that look like this, that are filled, that are benched.
Luke, sorry to interrupt you. Just letting you know that there are two different ways to share in Teams PowerPoint presentations, and we're currently not seeing the full screen mode. We're currently seeing like the behind the scenes mode, so we're not at the same slide as you. So if you just close down your full screen mode and just go back to the regular mode, that would be suitable. Yes, we can now see current examples page. Yep.
Yeah. All right. So this one here just shows what we currently see on a lot of sites now, where there's alleged controlled fill, benched sites, issues with retaining walls, part natural, part filled sites. Obviously, you can see by the cuts, we end up with moisture change in the soils. We have AS 2870, which provides us some of those answers, but through some of the research, various projects that both groups have done previous, we've found that there's a lot of variability in the solutions, the answers that we get from the soils versus the solutions that are in our standards. And quite often, most engineers are left to section 4 to determine it themselves. So what we're hoping through this project is to try and quantify and work out some of those answers so that we can already give or provide practitioners with further information on how these things can be worked. And at the moment, we have a current example, and this is a site that was screw piled, a filled site, but there's still been issues. There's been issues with settlement of the fill. There's been issues because depending on different structural engineers, up until now, a lot of people wouldn't necessarily tie in a screw pile to a slab, or they wouldn't tie in a board pier to a slab. So they're working for settlement, but up until date, there hasn't been a lot of research projects on how to actually control heave with a footing system. And up until this point, we have been looking at screw piles, and a fair part of this project is the interaction between the screw pile and the slab, so that when we get heave, how do we dissipate that heave so to not break the connection between the screw pile and the slab itself. And heave can be occurred by various different things. Heave can be occurred when trees are removed and we get rehydration. It can be from over-consolidated fill, like I showed just previously, and it can be from when we get leaking services. And all of these issues end up adding to the insurance costs of the building originally, but also then to try and rectify any of these issues, we also then end up with higher insurance costs. This is another site where there's been plumbing issues, and you can see that there's been a settlement of the fill. You can see that the slab there is actually just cantilevering over it. That's actually the corner of a house, and the plumbing's in there. The plumbing was completely broken below ground because it's just not built or designed to sustain the sort of movements that we get. We also have that there's been changes in requirements, whether it's local councils and things like that, into create green areas. And green areas mean houses that have trees. And that's trees in nature strips, and they can be front nature strips, it can be side nature strips. We also don't have control over what we have on our site or what our neighbours have. There's also been changes to the sewerage system, where water in trenches, particularly sewer trenches, that used to be accepted into the pit itself and kept the water level at a lower level, is now rising. And what we're finding on a lot of sites is that that water then lifts up and becomes hydrostatically charged or head charged from higher areas and will backflow up through service trenches on sites and underneath slabs. And that's something that gets quite regularly seen. We've also got areas where there's low lying that is being filled to build on. Now, the filling processes at this stage are not being completed as what would really be required. And that leads to then more use of board piers and suspended slabs, but it still doesn't help out if you get an over-consolidated fill, which quite in Victoria happens quite a lot in the northern and western suburbs because it's put in quite dry. So therefore it's susceptible to a leak and then heaving. What we're aiming for is a housing product that is more green and more environmentally friendly, and also, most importantly, great for the homeowner. The results of this project, the IP, will be free to all. No company, no association will own it. It is to be for the betterment of community and society. And the idea is to create a product, a house, that lasts. It's the biggest investment that most people make. After this project has been completed, we believe there will be substantially more research required to answer some of the questions that we have at this point, plus others that will come up. This could lead to changes in, instead of using foam waffle pods, recycled plastic, cardboard, there's various options. Governments, universities, we have spoken to them about that at this stage. Further research will be required to determine the appropriate design required for different soil conditions, different climatic conditions, and different soil activities. The next slide here just shows what trees do. Now, I've dealt with arborists before. That's a size 14 boot over the top of a tree, and that's going down to the bottom where you can see the edge of an oval, and all that tree wanted to do was get that moisture. And then if the tree's taken away, all that soil sucks up more moisture and heaves. And at the moment, we would all design a slab on board piers for that, but it only counts why the tree's there. Once the trees are removed, that becomes an issue. So we're aiming to develop a system that can be used by all, that will be cheaper, safer and stronger, and more environmentally friendly for our housing solutions. Insurance companies and the cost of any insurance is dramatically affected by the performance of the footings and the climate we all live in. If trees are planted, sewer trenches are filled with water and then backflow into houses, then we have a problem that needs a solution. And this is another final example of where you have trees. This is a typical sort of built up area where you can see trees have been allowed to grow at the front, and the tree roots, they do go to where that soil concrete interaction is, because typically moisture will get down there as you get cracks off the edge of the houses. The main aim of this project is to then develop a procedure or a guideline or a standard, and our intention would be taken up a bit like the AGS 2007 slope stability to overcome issues with changing of standards and the requirements of that, but it would be an industry deemed to comply solution that's been researched and backed up. And that's the end of my presentation.
Thank you, Luke. Really appreciate the insight and the fact that you highlighted the issue, the cause, and the challenges, and also the need for a solution. Really appreciate it. And again, like you mentioned before, let's leave the Q&A at the end. And to keep the momentum going, I'd like to welcome our next speaker, Russell Brown, representing the Foundation and Footing Society Victoria, who brings an incredible wealth of experience and passion for the industry. With 65 years in the fields of structural, civil, and geotechnical engineering, Russell has worked across a diverse range of projects and roles. And please join me in welcoming Russell, who will take us through a brief history of screw piles and the key reasons why a system like this is necessary to solve the current challenges. And over to you, Russell.
Okay, sorry for not understanding computers. There's a left-hand thumb that's doing it for me. Yes, I've been around a while, and I noticed in my summation of me, somebody cleaned out the fact that I am also a life member of the Beefsteak and Burgundy Club of Melbourne, which is one of the great achievements that I have done. Reason for raising it is that actually drinking wine eventually allows you to find out about screw piles in tension. And I will demonstrate that when you can see me. So if we go to my next slide so that we can get some time for Biju. Yeah.
Second.
I'm happy to wait. This particular slide shows you what is believed to be the history of screw piles. My goodness,
We're
that's
on
interesting.
speaker view. We're just seeing Russell.
Hold on, we'll stop sharing.
Go. So, okay. Just so that when you get to this slide, you'll understand what it is. Next one. This are light towers, and the story goes that the person who actually did this used to make propellers for the first ships that were going to replace paddle steamers. And of course, when they were casting their propellers, some of them didn't work. So they had a whole pile of propellers that didn't work. And somebody said, well, why don't we use them connected to timber from the forest, and we'll build a jetty. So the first use, they believe, was building jetties. And then they decided they'd use them for doing this instead of having boats having to float and do the same thing. You'll note that if you look at a storm hitting these, not only do they work in compression in the ground, but they have to work in tension. And that is the most important thing, because 2870, which all of our foundations are based upon, or hopefully they are, sorry, in my opinion, hopefully they're not, you then get a situation of heave. And the situation of heave, which I'll get to in this slide coming up now, it's a bit hard to see, but right on the one corner is a naught on unit C, and on the other diagonal corner is 188 millimetres. That slab, when we started to correct it, was 210 mils out of alignment. Reason, there's a little sewer line along the bottom of that sketch, and that sewer line had water in the trench, and that trench was 3.1 metres deep, and the clay was being swelled from 3 metres down due to water in that trench, lifting the building. The claim, of course, was that maybe that wasn't the case, but if you look carefully in the middle, there are trees. So those trees were actually drying out the ground in that location, allegation. My opinion was they already had. And the situation is Unit A, exactly the same construction. Graph slab, everything's the same. It was only out of alignment 22 millimetres. So at worst, the tree was drying out at that location 22 millimetres. So therefore, the 210 was 190 from heave of a plumbing problem. Problem, water in a government-owned trench. Therein lies your problem. Now, in 2870, better known as the code, you will see the diagram, bottom right-hand corner. What a tree does is on the red side, on the right-hand side of that diagram. What we allow for with no abnormality is a little wedgy triangle in the middle. What a leak can do is the green. Oh, what's in Australian Standard 2870 to handle that? Nothing. Full stop, nothing. Keep it in mind, it's not there. Therefore, 35 or 40 years ago, I did start using screw piles, using them to hold structures down, connecting them in and holding down. Here you can see Melbourne Water. Melbourne Water are very clever. They don't say when you build near their facilities, use a 1-to-1, which is the standard. Melbourne Water know their trenches are full of water, and that water saturates the ground, weakens it, and you can see that at 1-to-1, you would be almost actually in the trench. Melbourne Water push you about 5 metres away. That's how you handle water in a trench. So imagine you've just bought a block of land down there in Williamstown in a subdivision put forwards by the government. The width of the block is 10 metres. So if you've got to be 5 metres away from the sewerage authority, your house is now 5 metres wide. A marvellous situation. Next slide. Guess what? This is my house. No one else's, mine. To look at it very carefully on the right-hand side, or sorry, left-hand side of that photograph, is actually the edge of the concrete paving of the footpath out the front of my house. If you look very carefully on the middle of that photograph is what looks like a broken pipe going towards the right-hand side. Underneath it are 3 cables in. You'll notice underneath those 3 cables is where my stormwater pipe has now been pushed. My stormwater pipe and the pipe leading to the gutter is in fact 3 Telstra and NBN cables. Oh, how did I notice the problem? It took 5 years. And I noticed looking out of my front room that my front lawn was full of water and my house had heave. So we had to fix the plumbing, and that whole trench was full of water, sadly in this case, from water from my own roof. Problem is minor, it isn't. That is the effect of highly reactive soil being laid in a lake. The lake is salt water. The sodium mixes with the calcium, takes away all of the calcium, leaving you with highly reactive. You then get heave of the total teutonic plank and it dries out and you get exactly that. Then if you get wind-blown dust, it fills the cracks. So when you build on top of it all and it wets up, it can't move east-west, can't move north-south, it can only go up. Not allowed for. Thank you for listening, and I do hope you learned something.
Thank you, Russell. I definitely learned a lot. It was very insightful, and the pictures and case studies tells us all, and really highlighting the key engineering considerations and the industry applications as well. And you are definitely like very passionate about the solution, the requirement for a solution, and you continue to support the industry. So really appreciate it. And I guess now to continue our discussion, let's also hear from our research partners. Our next speaker, Rajeev from Swinburne University, has been instrumental in advancing research on this topic, and we can't wait to hear more about this project. And over to you.
Oh, thank you, Olivia. Can you hear me well?
Yes.
Okay, let me share the slides. Okay. Okay, I hope all can see the slides. As you know, the Luke and Russell has set up the problem and the issues of footing in expansive soils and how the conventional footings are designed and what's AS 2870 covers and where the issues are. So it has been summarized slightly. So what we are planning to do here is to support these, as you know, we just proposed the hybrid footing system combining the waffle slab with the screw piles, and screw piles drive down below the reactive zones depth, and then trying to understand how these hybrid footing system going to behave in extreme weather condition, and when it's and also the moisture changes happen due to pipe leak even underneath the slabs. So that's the main purpose of this research, and since we don't have much data on these type of footing system to design and then analyze the performance in the long-term moisture changes. So as you can see that the system has been combined, both screw piles and the waffles, and the screw piles goes down below the reactive zone depth, and then we will be analyzing the performance and understanding the performance. So as you know that in the research, so we have information about expansive soil behaviors and the conventional footing systems, and it has been monitored or documented in some level of accuracy, but it's not complete. So what we will be planning to do, and we are doing, is just collecting all those data and trying to understand what has been done and what's not, and where the informations are lacking, and then trying to understand what's in the current practice and where we can provide improvement with those new information or existing informations. And of course, it's the different soils, the fills and the expansive soils behave differently. So we're trying to do some additional laboratory work on different type of expansive soils and trying to establish the behavior in extreme moisture changes and weather conditions. And also we will be doing some field monitoring, long-term field monitoring of large-scale slabs with and without these hybrid footing. That means the combined screw piles and the conventional footings in the same location, and then understand the long-term performance of these slabs and how well these hybrid footings perform compared to the conventional ones. And those information finally goes into the computational model to simulate the long-term performance of those footing systems. So I will show you some of the field monitoring work we are planning to do. We will be casting the large-scale slabs with screw piles and without, and also putting a lot of moisture sensors and pressure sensors to understand the heave pressures and when it shrinks, and how the slab's going to be supported and what's the pressures going to be on underneath the slabs during wetting. And also we will be monitoring the ground movements and how it's going to be in control wetting activities, and also the normal weather changes. And there are other ways of monitoring moistures using neutron probes and other technologies techniques. And then we will be collecting the large testing data for expecting to monitor for more than 3 years. And though from those informations, and parallelly we will be developing computational models. As you can see, some of those model has been already developed on the heave and edge heave and the center heave phenomena. And then using the soil properties and the climate data, we will be performing the long-term moisture variation with different combination of weather patterns, and we can predict for long. This is just a sample of some of the work initially I have done, and those information will be feed into the computational model, and the soil will be modeled for shrinking and swellings. And I don't want to go too deep into how we are going to simulate the soil behaviors, but you can see from some of the equations on the volumetric swing changes in the soil domain, and can be captured with the moisture changes on the soil. So that's the way we will induce the swelling pressures, or when it shrinks and drop the support underneath the footings. So that's how we will be simulating the extreme scenarios and understanding those performance in long term. And these information will be used or go into the new development of 2870, or maybe a guideline for the practicing engineers to use. So what from here, I will let Biju to take over and to show what we have done on understanding the screw pile performance, and then we can discuss about what's going to come next and what's the plan for the future works. So that's all from me at this stage, and I'm happy to take up questions in the later stage. Biju. Yeah.
Yeah, thank you, Rajeev. I'll share my screen first.
Oops.
Let me put it into the bigger screen 1 second. Thank you. I'll just quickly explain the work we have done already, which is basically looking at the screw piles, because as Rajeev explained, there are two systems going to make the hybrid waffle. One is, of course, the screw piles, which is trying to hold down the slab. And the second one, of course, the slab system, which is going to work against the heave. So the initial study was mainly looking at the behavior of screw pile. As you know, screw piles have been extensively used in the Australian construction industry, but not much research has been done to model the behavior. So the first attempt was to understand the screw pile behavior. So what we have done is we have installed around 28 test piles in Kuvirab. As you can see, the pattern of the installation. So we made sure that it's all installed in a grid, so that it is easy to test them with minimum reaction piles. And we've installed the screw piles with a 8-ton machine, and then we engaged 3 contractors to do that. And the other thing we did is we measured the torque. As you can see, this device, which is attached with the drive motor, so that could provide us the useful information of the torque. So I'll show you the measured torque values later. And we have installed actually 8 different types of piles, based on the depth and the helix sizes. As you can see, there are 4 types of helixes we used, and also we varied the depths to get the different combinations. And so this is the data we collected when we installed the pile. As I said, we used a device called torque up, which you can see attached at the bottom of the drive motor, and which gives you the useful information. And this is an example of such data collected, because this is a pile which was installed up to a depth of 5.8 meters, and these are the torque readings. So at the moment, we are going to an exercise of understanding, what this means to the final capacity of the screw pile. For example, at the moment, there is a current method, which actually predicts the capacity of the screw pile from the torque reading, the final torque reading. So we are checking whether, how that is, that information is correct, whether that gives the correct values. And also we are looking some other analysis as well. And after installation, we test the piles. We did the compression testing and tension testing. And there are 2 setups. As you can see, this is the compression testing setup where your jack is below your reaction beam, so that when you operate the jack, the pile will be pushed into the soil. And whereas this is a tension testing setup where you put the jack on the top and you connect the pile with a rod, and so when you operate the jack, you will be actually pulling out the pile. So we did these both tests on all those 28 piles. And the other thing we did is we collected all the data with a data acquisition system, so that we get the values every second, and then we plotted those results. And the other important thing is the measurements are based on an independent frame, so that we get accurate values without getting affected by the other systems. This is the data we collected. For example, this is for a particular pile, which is the pile which was installed up to 5.8 meter deep. And then we did a tension test. And then we measured the deflection and the load. And we plotted the graph. And this is the raw data we get from the data acquisition system. But as you can see, it's very difficult to analyze that data. So what we did is we sort of fit curve, and you can see we could fit a logarithmic curve very accurately. And then once you did that, then we can do further analysis on the curve, looking at different failure theories and other patterns. For example, this one, as there are different failure theories for screw piles. For example, Davison 1972 offset method is a popular method which is used to predict the failure load of a pile, and there are so many other theories as well. So we could really look at which of these theories are give better values for in our particular project. So that is the current work which is happening at the moment. We are going through all this data and plotting these graphs and analyzing the data, so that we get a good idea about what theories we can sort of adopt when we are going for the field monitoring and designing those field monitoring tests. And also, after the testing, we removed all the piles to make sure that we understand, how, because normally what happens is once you install a pile, no one will be able to see what happens in the ground unless you pull it out. And it is impossible to pull out a concrete pile. But screw piles, one advantage is you can pull it out, and even, that is one advantage, the recyclability of screw piles. Anyway, we pulled out all the piles which we have tested, and we did a examination of the weld and to understand how these plates behaves. And what we have found out is that very rarely you get a structural failure of the screw pile. Most of the time it is geotechnical failure, which means deflection. And that is all from me. And this happened because a lot of volunteers from ACSEV and footing FFSV came and helped us, because otherwise it's a massive project. Installing and testing screw piles is not easy. But thanks to all the volunteers who sort of participated in this research, and without them, I don't think we would have achieved this. That's all from me. Thank you.
Thank you, Biju. Appreciate it. We do have a question in the chat, but like I mentioned before, let's open the floor for questions. Again, thank you to all the speakers for that insightful presentation and sharing the journey, sharing your knowledge and experience. And now let's open the floor for Q&A. And I encourage everyone here to ask questions and make the most of this platform. So please drop your questions in the chat and I'll read it out. Or if you'd like to ask a question yourself, feel free to raise your hand. We do have a question for Rajeev and Biju. Can the screw pile be tested dynamically rather than statistically? Presume a dynamic test can provide the results immediately.
Biju, you want me to answer, or you?
Yes.
So this, it's a good question, but for this particular problem, and the moisture change and the pile movements is very slow process. It's not a dynamic process like very fast. So in that sense, there's no need for applying the rapid load or load reversals. And if it is a different application, say machine footings and all, and then it's need to be checked for different vibrational load with different frequencies. But I'm not quite sure that how far this is relevant to this particular problem on testing dynamically on this pile. And then also it all depends on what's the frequency range we are going to use for dynamic load test. So this particular problem is very slow process. It will take minimum 3 to 4 weeks for the moisture to infiltrate through the depth, and then the soil to start to react on those moisture changes, any changes due to moisture. So I don't feel, and then dynamic test also, it's what parameters we are planning to test. That's important. It depends on what's the application of the screw piles, and then it's determined what type of test to be performed. I hope that's answered Yuchin's question.
Yuchi just gave a thumbs up. Thank you.
Oh,
Cool. Any other questions from the audience here?
Can I add to the answer that was just given?
Yes, please.
Dynamic testing, as I understand it, virtually measures compression or axial load downwards, correct? Or can it actually be used in reverse, working out uplift forces? That's my question to the question. The point I'm making here is that we all understand fairly well what a screw pile can do based upon some fairly crude readings. And those crude readings allow us to know that we're safe, maybe not secure, but remember, you've got to order your screw piles, you've got to put them on site, you've got to put them in the ground, etc. And there's an enormous amount of conservatism in most people who put screw piles in. The point being, do we really need to dynamically test for their compression capacity when in fact what's causing failure is tension loading, i.e. heave? If you want a rough figure from my experience over the last 40 years, 80% of failure is caused by heave, for which 2870 says nothing. Therein lies reality. Therefore, why would we want to do an accelerated test to verify something that really we don't even need to know because we already know the answers from past experience? Unless, of course, as I think was said, if there is a reason to want to load this thing, perhaps put a crane on it, and therefore you want to know what its capacity is instantly, yeah, I can understand dynamic testing. But a house is going to be there for 50, 100 years, and it might take 3 to 10 years for a leak or a tree to start affecting it. I really can't see the point of wanting or why you would use dynamic testing for light structures. By the way, those comments were not from ACSEV or from Foundations, they were mine.
Ah, that makes sense. Yep. Thank you, Russell. Dr. Burt, you've got your hand up.
A question to Rajeev, I guess, in particular, just wondering from the structure performance viewpoint, what would be the sort of concrete strength that would be required?
So in the normal construction, I think it goes up to 30 MPa concrete in the wall slab. That's what is normally used, but in this particular problem wood and since the pile is going to be, the screw piles is going to be in tension and compression, so we have to be mindful on the tension forces at the connection and how the connection going to behave within the concrete. So that's need to be studied, and the swelling pressures can be significantly high, and this can create stress concentration at the connection point. So we need to check, but in the normal construction, I think it's 30 MPa concrete normally used in the waffle slab. So we have to, of course, in this particular case, need to be studied for the connection behavior of screw pile and the waffle slab. Yeah.
Right. Thank you, Rajeev.
Thanks, Will.
Thank you, Rajeev. We have a question from Jet Fletcher. Two questions, actually. Number one, are you investigating the use of crushable styrofoam or the like under the waffle slab platform to manage heave forces onto the slabs?
Yes.
And second question, are you investigating improved moisture stability control at the level of underside of waffle slab beams, particularly at the building edges? Better backfill spec and exterior wall runoff control would help.
I think, Russell, you are muted, Russell.
God, how
Yeah.
the answer in that question is no, we are not looking at it. I, for years, experimented with drip watering systems to control movement, and I was very successful until such time as we realised that cats, dogs and rats can eat most of the drip watering systems, and therefore they have a lifetime of maybe 5 to 10 years. So control of moisture in the ground can be done, should be done. However, it's a complete waste of time when somebody sells their house and someone else buys it. That's what we found. I used it for a couple of projects under the Housing Guarantee Fund. We got superb results. In fact, the best result, which caused me no end of happiness. An elderly Italian gentleman used to go under his house where he had his tomatoes and his olives and all the rest of the paraphernalia, and he would adjust the drip watering, and he'd water each and every stump under his house so that every door in his house worked perfectly. Sadly, he died, and his son wanted to sell the house, and he said, I don't want to do that. What will make it work forever without having to juggle the water? Juggling water, yes. In fact, Biju is going to be doing it for his house soon, but he doesn't realise how rapidly he's going to learn about it. But the point being, it is an excellent method of correcting a problem. Long term, it's incredibly difficult to make sure it keeps working.
Mm.
Okay.
Okay.
Sorry, Jeff.
Wood, you are muted.
Yeah, just a follow-up question on that. With the effort, I guess, to keep the soil moist, would oversaturation be creating a problem? That's a question to Russell.
The answer is yes. Oversaturation creates a range of problems. It gets you into that green area on that graph that I put up, or the diagram that I put up, and the wetter and wetter your soil. I think what most people don't really grapple with is the 3 phases that a soil goes through. In Melbourne, builders like to build during summer, it's dry. So the soil has got vertical cracks, and the horizontal cracks are gone because they run their trucks over it. Okay, so here you have building on a dry soil, and they push sand onto the site, fill the vertical cracks. But if they don't do that, wet it up, and the soil expands laterally and very little goes up. You then get to that stage where you've got a mixture of air, water and soil, which is your mid-range. Add a bit of water, you get a little bit of expansion laterally, and you get some movement vertically, etc. However, get yourself into the next phase. Everything is wet, There's no air left. Add water. The only thing that can happen is the soil goes up 3 times more than it goes up when it's dry. There's your problem for the same percentage change in moisture. That's the problem. Nobody thinks through. You're not testing a soil in the oven. You're not testing a soil in a laboratory. It's in the field. In the field, when you get above 30%, 33% moisture, add water to that soil, it only goes one way, and that's up. Worse, a tree will dry you out basically down to about 1.5 metres. And if you read Beadle, you'll find it's abnormal in the extreme for a tree to be drying out at depth. A tree root will go to depth looking for moisture. A tree will not go down and dry ground out. It's too much work. But a leak in your services at 3 metres deep will lift your building 200 mils. That's the problem, not the theoretical answer that I think you might have been looking for. The practicalities are, when your moisture level gets above a certain figure, every time you add moisture to that soil, it only heaves. It never goes east-west, and it never goes north-south. It only goes vertical. Failure. What did I say before? 80% of failure that I see is linked to heave. And of that 80%, add another 10% for rehydration when you take a tree out. So the only time a tree causes you major problems is when you cut the big buggers down, pardon the French. Does that answer your question?
Thank you. Thank you, Russell.
Thank you.
Thanks, Russell. For myself, I'm interested in the industry adoption side of things. I understand that this project aimed to develop design guidelines or building practices for hybrid footing systems. So was just wondering, any key things that we need to keep in mind, or what challenges do you foresee in getting these guidelines adopted into the industry? For example, industry standards and building codes.
Can I answer that just again? I'm sorry, I'm hogging it a touch. But Foundations and Footing Society, having already found out over the years that whilst AGS does an excellent job for major projects, most of the AGS participants are not really that interested in light domestic construction. And the reason for that is there's no money in it. I mean, the cost to go out and drill a hole and test for a house, there's no money in it for the bigger firms with high overheads. Therefore, we don't really have good codes, if any, for actually testing soils, etc., for housing. So the basic thing Foundations has already done is we have written 7 codes of practice which cover an enormous amount of how you should test, what you should do, how you should do a whole range of things. So we have 7 of them, and our intention would be, when this project is at least long enough into its teeth, to put out how to design for a house for screw piles holding it down with the capacity for the soil to swell into a void so that you don't get uncontrolled heave. Okay? So, yes, we are ready, inverted commas, to do a code of practice by Foundations and Footing Society. I would guess ACSEV will sanction it as well. And then if Australian Standards wants to use it, fine. But waiting 11 years for them to get round to doing it, I shouldn't be saying this in public, it ain't worth the wait. The loss per year is much too high to be waiting for the enormous code committee problem to get around to fixing it.
Yes, 100%, I agree. Thanks for your comments. We have 5 minutes to go. Any other questions from the audience?
Can I just demonstrate where you first learn about screw piles? As you can see. Right? And the reason is, you will note it doesn't help you in compression. It is strictly a tension member. It is solely for tension, and the result can only be reversed if you use a Chinese chopstick to push it in. So the first real use that every human in Australia maybe understands, but has never actually really is your classical genuine helix cork remover for your wine.
It's a very good illustration. Thank you,
Just thought
Russell.
I'd use it, and the result is worth having.
Yeah. And enjoy your wine and celebrate the collaboration today.
I hope somebody approves it.
Yes,
Right.
thanks. And before we close, I would also like to understand what are some of the key next steps in this project.
Can I answer that? Or okay, we have already one main site that is saying yes to us, and the conditions may need some negotiation. 3 years may be a little too long for them, but that may mean we need another site. It's the Boeing Reserve, Moonee Valley Council. We also have an offer from ARC, and we didn't want to go testing their site until we had a better site somewhere else, because the ARC site will be 2 slabs on it. We can't get the 4. So we will be looking at 2 sites, and we've got a third in the making in somewhere we're hoping to get an answer there. Can't use them all, and styrene pods and going for something else. They will probably have some sites willing to use if they will pay for them to be used. So we may actually end up making, which of course would be a marvellous result for a non-for-profit organised. So acquiring and getting agreement to use sites so that we can actually do the testing that we think is needed.
Yeah, thank you.
The long-term testing can be implemented. Okay, so.
Thank you, Russell.
You're
Sorry,
mute.
you were
Sorry.
Cutting out a bit. I'm not sure whether that's my side or.
No, it's for all, I think.
Oh, okay. Sorry, I wasn't sure it was because of my internet or it was for all. But
It's
thank you,
yours.
Russell, for sharing the insights. And any other comments from our speakers before we close?
Oh, good.
Okay, all good. Yeah, thank you again for everyone's sharing and participation, and for our first session of the year for Engineered Solutions, and that was a really informative session. A huge thank you again to all of our speakers, Luke, Russell, Biju and Rajeev, and for sharing your expertise, and to all of you, our audience here, for engaging in today's session. And again, just a final reminder to our audience, if a question comes to mind later, please feel free to reach out through email. And Natalie, do you mind to pop the email in the chat. So it's info@smartcrete.com.au. Oh yes, Natalie, thank you. Please have a look at the email in the chat, and we'd love to keep the conversation going. And I really look forward to seeing you all in our next session as we continue to explore more innovative solutions in concrete technology. And thank you very much again, and enjoy the rest of your day. Thank you.
Thank you, Olivia.
Thank you, Olivia. Thanks.
Thank you.